Okay, we're given the vector function that you see here. Not going to read it to you. It should be, well, that's z squared over x. I think everything else is pretty easy to read, and I don't think that's bad. And we're asked to find the divergence and the curl of f dot n for a unit sphere. Okay, well, let's just do that. The divergence, of course, we're dotting the partial with respect to x operator with the x component. In other words, we're taking the x derivative of this function, and we get e to the x sine of xy plus y e to the x cosine of xy. This is all from the I component. Okay, from the j component, well, we dot the partial with respect to y operator with the j component. There's no y dependent, so the j component contributes nothing to the dot product. So these two terms come from the product rule when we take the x partial derivative of the I component, and there's nothing contributed by the j component. The z partial of negative xyz is just negative xy, so right there is our divergence, del dot f. Okay, the curl, yeah, we can always calculate the curl using the distributive law and knowing what how the I, j, and k vectors dot with one another. I'm sorry, how they cross with one another. They dot product is always zero, but right-hand rule tells us what we get if we cross I with j or k, or j with I or k, etc. And if we have only maybe two components of at least one of the vectors, sometimes it's more convenient to use the distributive law and just do it that way. But completely equivalently, we can do the determinant, and we all know the determinant form of the curl, so that's what I used here, and I believe I got the right function here. Okay, so here's the curl, and if I'm wrong about that, you can calculate this probably more accurately than I can, because you're a little more careful, maybe a little more clear-minded, but I think I've got it right. Okay, now that's the curl. We've got the divergence. We want to do the curl of f dotted with n, and we're going to be asked to also integrate the divergence over the unit sphere. So here is what we know about the unit sphere. Okay, the unit sphere can be represented in terms of x, y, and z by the equation x squared plus y squared plus z squared equals 1. This is a level surface for the function x squared plus y squared plus z squared. So if we want to find a normal at any point, we can take the gradient of x squared plus y squared plus z squared and get an equation for a normal vector. That's one thing we can certainly do, and we actually do that here. Okay, we do the gradient of x squared plus y squared plus z squared. I threw in the -1, but it isn't necessary. It's a constant. It's not going to contribute anything to the gradient, and it's, this is some function of three variables equal to a constant. Doesn't matter what the constant is, the gradient is going to be what it is. So the gradient is just xi plus yj plus zk, and we normalize this normal vector by dividing by the magnitude of the gradient. Okay, didn't see the gradient there. I was wondering where that -1 came from, but the x squared, y squared, and z squared also. Okay, and the gradient, again, being just xi plus yj plus zk, its magnitude is just the square root of x squared plus y squared plus z squared. So here we have not only a normal vector, which is the numerator, and that's just one possible normal vector. Any multiple would also be normal. But we also have normalized it to where this is a unit normal. Okay, so just using this form, we get our normal vector. Now we can do something else. We can parameterize the sphere. Now I've just parameterized here the upper hemisphere, because that's all we're actually going to be using when we do an integral of the curl. I think that's the way it's stated. And our function is just xi plus yj plus zk. Now that's a parameterization that gets us to the point xyz, from the origin to the point xyz. Now, since we know that x squared plus y squared plus z squared equals 1, we can solve for z, and we get this. Okay, and now we have a vector function that takes us to a point of this sphere. Solving for z, we get square root of 1 minus x squared minus y squared. You should be very familiar with that by now. And here we have it. Now, if we parameterize the unit sphere by this function, x squared plus y squared plus z squared set equal to 1, this level curve of the x squared plus y squared plus z squared function, then we need to describe the unit sphere by inequalities. And one way of describing it that way is x goes from negative 1 to 1, y goes from negative square root of 1 minus x squared to the square root of 1 minus x squared, and z from negative square root of 1 minus x squared minus y squared to the square root of 1 minus x squared minus y squared. I'm not going to discuss that because we've done that already, and again, we should be familiar with ways to parameterize spheres. And I believe we are. Okay, so this is the set of inequalities we need to use if we use this functional equation to describe the sphere. If we describe it in terms of parameters x and y, we only need to mention the restrictions on x and y. And x goes from negative 1 to 1. Y will go just as it did here, from negative square root of 1 minus x squared to the square root of 1 minus x squared. Okay, there are other parameterizations we could use. We could use cosine theta I plus sine theta j plus the square root of 1 minus cosine squared. I'm sorry, it wouldn't be just cosine theta, it'd be r cosine theta I, or let's say a cosine theta I, where a is the radius of the circle. A is the distance from the origin to our point xy in the xy plane. So it'd be a cosine theta I plus a sine theta j, and then the square root of 1 minus a squared cosine squared, a squared sine squared, adds up to just a squared, 1 minus a squared times k. And our parameters would be a and theta. Or if you want to use t instead of theta, you can do that. Okay, well, there are many ways to write this parameterization. This is a way I chose, but we've seen alternate ways to write the parameterizations. According to this parameterization, let's come down here and see what this tells us about our normal vector and our integral. Well, Rx, the x derivative of r, is this, and that's easy to verify. Ry is this. So a normal vector could be Rx cross Ry. And that's going to equal what you see. And in this case, I did the cross product just using the distributive law. I cross k is negative j. So I'm going to get a negative of this times j, which gives me the, well, just this without the negative multiplied by j. And there's nothing else, only an I cross k is going to give us a j, and there's not going to be a k cross I when we do this because I is missing. So this makes it fairly easy to do the cross product. Then we of course have I cross j, and I cross j is just k. So here we have this term and this term. Then we have the k term dotted with these two components. And k dot k, of course, is 0. I'm saying dot and I mean cross. I cross k is negative j, giving us this. I cross j. I'm not sure whether I said dot or cross, but since I just said a dot, I'd better correct it. I cross j is k. Then k cross j is what? Well, you know, right hand, k's up here, j's here. K cross j is in the negative x direction. So we're going to have the negative of this multiplied by the negative by I. We're going to have negative x over the square root multiplied by negative I, so the negatives go away, and here's what we have. So there's our normal vector, okay? And then if we want to integrate with respect to x and y, according to this parameterization and this set of equalities, all we have to do is integrate ds, of whatever it is, with ds dot n dy dx, okay? If we want to integrate the normal component of something, we're going to dot it with this, because if you dot a vector with n, you get the component of n in the direction, or you get the component of that vector in the direction of n, multiplied also by the magnitude of n. The magnitude of n is your multiplier when you go from your area down in the plane up to the area on your surface. Again, we've talked about this somewhat extensively, so I'm not going to redevelop the whole discussion. So you could say that the ds is n times your dA, your area integral, your dy dx. Okay. Now there's a relationship between this version of ds and this version of ds. Okay. Your vector ds, your vector area, this is a vector whose magnitude is equal to the area of your ds increment of the surface, the area of your increment of the surface, your ds area, is equal to the normal component, the unit normal times ds, where ds is the area of this increment, which you get by multiplying the dA, the area down in your xy plane, by the magnitude of, it turns out to be n over magnitude of n dot k. And that turns out to be this. This expression here, as we've seen again, is what you multiply by this area to get this area. Okay. Now, you can compare this by also noting that this n vector is just a little n vector divided by n dot k. And how do we get that? Well, here we've got the big N vector, here we've got the little n vector. Okay? Little n dot k is just k component, which is z divided by the square root of x squared plus y squared plus z squared. Okay, well, if we divide this by z over the square root of x squared plus y squared plus z squared, and the algebra is actually very simple, it turns out that what we get is just this. Of course, to get this, we're going to be getting a z in the denominator, but remember that z on the surface is the square root of 1 minus x squared minus y squared. So I kind of recommend you maybe replay what I just said and work it out. Convince yourself, because these interrelationships help us understand more deeply what it is we're doing when we do a surface integral.